Okay, this topic will be discussing on the reversible elementary reactions and equilibrium constant. So the keywords over here is reversible and elementary. So in the reaction, if let's say that a product is formed and the product can in turns actually react together and give back your reactant. So this reaction is reversible. So in other words, it means that if, for instance, like A plus B, which is your reactant to give you a product, which is C, and your product can react back to give you A plus B. So this is a reversible reaction. So for instance, we look at the reversible reaction. So I say highlight the keyword reversible. So reaction can be separated into two concurrent elementary reactions. So we are looking at elementary reactions. So which means to say that the order of the reaction is the same as the stoichiometry of reaction. So we break it down into two reactions. One is the forward reaction and the other one is a reverse reaction. The forward reaction, we have a rate constant of K1. Reverse, we have a rate constant of K2. So for instance, we look at here in N2. So this is N2 is a reactant in the forward reaction, but it's a product in the reverse reaction. So reactant in the forward, because N2 is a reactant in the forward, but when we look at it in the backward, this becomes a product. So the rate of disappearance of N2 through the forward reactions is this. So we have to look at here. We look at the forward reaction. So for forward reaction, okay, so rate for the disappearance of N2 will be K1 N2 and H2 3. So this is your forward reaction. So similarly, we can do the same for reverse reaction. So for reverse reaction, we look at ammonia. So the consumption of ammonia is K2 and H3 to the power of square. So this is the, because it's an elementary reaction, so the order is the same as the stoichiometry. So both reactions will eventually reach a equilibrium point. So which means to say that if you have a reactor, the concentration of N2, H2 and NH3 will remain unchanged after a certain point. Yes, initially you may charge in N2 and H2 into a reactor, but over time NH3 will form, but more NH3 form, you'll go back to N2 and H2. So eventually, until a certain time, the concentration of N2, H2 and H3 will remain constant. So when this is so, it means that the forward reaction will be the same as the reverse reaction. So which means to say these two, they are equal. So forward reaction and the reverse reaction, both of them are equal because this is only at equilibrium. So take note, when I say that this is equal, it's only at equilibrium. If they are not equilibrium, these two, they are not equal. So by doing so, we can rearrange it that K1 divided by K2. I just bring this to this side, K2 to this side, and I'm going to bring these two terms to the right side. So this is times, when you bring over here, it will be divide. Okay, so now you see over here we get a ratio of K1 over K2, and then we get this term over here, which is very familiar to most of us, because if you remember that in the past we say that N2 plus H2 give NH3, and you have seen a value K, which is your product over reactant. Right, so you look at here, this is the same as this, and this is your equilibrium constant K. So equilibrium constant can be defined by this expression over here, which is product over reactant, or the forward rate constant divided by the reverse rate constant. So what we have go through is I have shown you how do we actually come up with the expression of this equilibrium constant K. So first step, write the forward reaction. Second step, write a reverse reaction. Then set these two rate to be the same at equilibrium condition, and put these two terms, equate them together, rearrange, you get the equilibrium constant K. So in the assessment, you might be tasked to derive this equation over here. So you are expect to show these steps over here. So with this, we will look at the example 2.5. So the dissociation of phosphorus pentachloride PCl5 proceed through a following reversible elementary reaction. So the keyword is reversible elementary reaction. And how do we spot for reversible reaction in a chemical equation? Look for this double arrow. So this is our reversible reaction. So initial concentration is 150 kilomole per meter cube. At equilibrium, this amount 65 kilomole per meter cube is dissociated. We are not talking about this as equilibrium concentration. This amount is being dissociated. Given that the rate constant for the reverse reaction K2 is 0.56 meter cube per kilomole per hour, calculate the rate constant of the forward reaction K1. So how we go about solving this question? So we write this reaction equation out. So initial, change, and at equilibrium. So initially it was mentioned that we have 150 kilomole per meter cube. So initial, we have none of these two, but change is at equilibrium, this amount is dissociated. So which means during the change process, there's a deduction in the PCl5, and this will give you the additions of 65 kilomole per meter cube. And at equilibrium, you have 85 kilomole per meter cube, 65 and 65 kilomole per meter cube. Okay, from here we are supposed to calculate the forward reaction rate constant K1. So we go back to the term that we just derived over here. K is K1 over K2 product divided by reactant. So we use this. K1 over K2, which is your product over reactant. So for this, the product is PCl3 Cl2 over reactant PCl5. And do note that we are using equilibrium concentration. So PCl3 we have 65. Cl2 also has 65 kilomole meter cube. PCl5 we have 85 kilomole per meter cube. And K1 is the value we want to find. K2 is given by 0.56 meter cube per kilomole per hour. So with this, we can solve for K1, and we must take note of the unit over here. So we solve for K1 to be 32.30. And now what's the unit? If we do not know, we can do a unit analysis. Meter cube kilomole per hour, and you'll get 32.30 per hour. So this is K1. Okay. Now we are supposed to determine the value and unit of equilibrium constant K. So from here, equilibrium constant K, as we've seen from what we have derived earlier on, K is K1 divided by K2, and K1 is we have calculated to be 32.30 per hour. K2 is given by 0.56 meter cube per kilomole per hour. So the per hour, we can cancel it off. K will have a value of 57.67, and with this you will have kilomole per meter cube. So this is the value of K, equilibrium constant.